Good morning, students. Hope you are all well at home. Students, I am your Ranjeet sir and I will be conducting your physics classes today onwards. First of all, the first term syllabus. There are 4 chapters. Chapter number 1, that is force. Chapter number 2, that is work, energy and power. Chapter number 3, that is machine, and the chapter number 7, that is sound. So these 4 chapters are there for the first term. The first chapter force that we have done in the classroom. Now today I am going to start with the second chapter. Chapter number 2, that is work, energy and power. Okay students, first of all, let us start with the topic work. What is work is? In our daily life, the work is used for some sort of exertion or the activity which we performed, like while writing, reading or eating. We say that we are doing work. But as far as physics is concerned, the work is said to be done only when a body moves under the influence of a force. And if there is no displacement of the body, even when a force acts on it, the work done said to be 0. Or we can write that work done is equal to force into displacement. Now the SI unit of work done is joule. That can be defined like the SI unit of force is Newton. Displacement is meter. So we can write 1 joule is equal to 1 Newton into 1 meter. Now the question can be asked to you, define the SI unit of work. Means that is 1 joule. Now how you can define it? The SI unit of work. The work is said to be 1 joule when a force of 1 Newton displaces a body through a distance of 1 meter in its own direction. So work is a scalar quantity. Means it has magnitude but not direction. Like students, let this is a horizontal or plane surface. A body is lying on it and a force F is applied on it. Let the body is at position A. When the force is applied on it, the body displaces through a certain distance. Let that is B. So the distance between A and B is S. So we can say that when a constant force F displaces a body from position A to position B along its own direction, then the displacement of the body is A, B, and the work done is F into S. Now move to the next, that is expression of work. That is W is equal to Fs cos theta. Now we can find the work done by finding the component of displacement along the force. By finding the component of displacement, the component of displacement along the force. Now this is a horizontal surface and one plank is inclined on it. Let AB is the horizontal surface and this is the inclined surface, and let this is C. Now the angle between AC and AB is theta. Okay, so suppose a constant force F acts on a body along AB. This is the body, and displaces the body on an inclined surface from A to C. The displacement of the body is AC, and that is S. Which is at an angle of theta to the direction of the force. Now to find the component of displacement in the direction of force is that along AB we have to draw a perpendicular CB. Let perpendicular CB on AB. Then the component of displacement in the direction of force AB, hence work done, that is equal to force into AB. What? In right angled triangle ABC, cos theta, that is equal to base upon hypotenuse. Base means AB and hypotenuse means AC. So that is equal to AB upon AC. Now we have to find AB. So AB is equal to AC cos theta. Now you can put the value of AB in this equation, that is W is equal to F into AC cos theta. Now AC, that is S, so this is S cos theta. That is work done, that is equal to force into component of displacement. S cos theta is the component of displacement in the direction of force. Now like this we can find the component force along the displacement. That will be like this: F cos theta into S. So these are the two ways by which we can find the work done by finding the component of displacement along the force and along the displacement. It is along the force applied and it is along the displacement. Now move to the next. It means we can say that the work done depends upon the magnitude of force, the magnitude of displacement, and the angle between the force and displacement. Now there are some special cases. First of all, case 1. Now we know that work done is equal to Fs cos theta. Now if theta is equal to 0 degree, then cos 0 degree, or you can say that cos theta is equal to 0 degree and cos 0 degree is equal to 1. Then work done will be equal to Fs cos 0 degree, and this is equal to Fs into 1. This is Fs. Now when the theta is 0 degree, we can say that the work done is positive. Work done is positive, or even we can say that the work done is maximum. Now the question is, when the work is said to be positive or maximum when the theta is 0 degree. Some of the examples, like in freely falling body, the mass m under gravity through a height h, let it fall from A to B. The force of gravity, that is like, let the body is a body of mass m is allowed to fall from A to the surface B. Now the force of gravity, that is F is equal to mg. Now the direction of the motion or the direction of displacement, that is vertically downward direction, that is h. So work done in this case, we know that work done, that is F into S. So here F is mg and S, that is h. So in this case, positive work done by the force of gravity in freely fall. This is one of the examples. Like students, we can take another example. Like we can take a case of pulley. Pulley does work on the load. Like this pen is lying on the table and I'm supposed to lift it up against the force of gravity. Now both the force exerted by me, that is mg, and the displacement that is in the upward direction, and let that is H. The work done by me in raising this pen, that is equal to W is equal to Fs, and that is equal to mg. So we can relate this example with pulley also. While lifting the load, the pulley does work. The work done by the pulley in raising the load, that is equal to W is equal to mg H. Now the second case number 2, when theta is equal to 90 degree. We know that work done is Fs cos theta. Now Fs cos 90 degree. So we know that cos 90 degree, that is equal to 0. So work done, that is Fs cos, that is simply 0. So this is 0 only. So we can say in this case the work done is 0. Now let us take some of the examples. First of all, we will take an example of pulley walking on a horizontal ground while carrying a load on his head. No work is done against the force of gravity because the displacement of load is normal to the direction of the force of gravity. It means the angle between the load and the direction of the force applied is 90 degree, which is vertically downward direction. So in that case, no work is done. But the pulley does work against the force of friction when he moves with the load. Let the pulley is moving in this direction and the force of friction that is acting in the opposite direction of the motion of the pulley. So pulley does work against the force of friction, but it does not do any work against the force of gravity because its displacement is normal to the direction of force, that is gravity. Now you can take another example when a body moves in a circular path in a horizontal plane. So no work is done since the centripetal force on the body at any instant is directed towards the center of circular path and the displacement at that instant is along the tangent to the circular path. Like, let this is the center of the circular path and this is the radius. As we know that centripetal force is the center seeking force which is acting in towards the center, that is F, and the displacement is normal to the direction of the force. Let this is O, this is A, and the angle between the displacement and the force is 90 degree. So again, if the angle is 90 degree, so Fs cos 90 degree, that is 0. So we can say that it is for this reason that in a circular path, the kinetic energy, hence the speed of the body, does not change although the force acts on the body. So 0 work done by the centripetal force in a circular motion. Okay. Now move to the case number 3, when theta is equal to 180 degree, or work done, that is Fs cos theta and Fs cos 180 degree. So cos 180 degree, that is equal to -1. So here it is Fs into -1. The work done is Fs, that is negative, or the minimum work done. Negative or minimum. Now we can take some examples. When a body moves on a surface, the force of friction between the body and the surface is in the direction opposite to the motion of the body. Therefore, the work done by the force of friction is negative. It is like this. The body is moving in this direction and the force of friction that is acting in the opposite directions, making an angle of 180 degree. So we can say that the work done by the force of friction is negative. Now we can take another example. When the ball is thrown upward, like this is the surface and the ball is thrown from A in the upward direction, and it reaches at point B. Now the force of gravity that is acting vertically downward direction, that is mg. Now the displacement h, that is upward, is opposite direction of the force of gravity. The displacement h, it is in the opposite direction of the force of gravity. So the work done by the force of gravity, that is mg, in displacement h, it will be equal to -mgh. So students, there are 3 special cases when the work is said to be maximum or positive, or the work done said to be 0, or the work done said to be negative or minimum. Now let us move to the units of work that we have done. So there are bigger units of work like kilojoule, megajoule and gigajoules. In order to solve the numerical problems like 1 kilojoule is equal to 10 raised to power 3 joule, which you have to learn. 1 megajoule, that is equal to 10 raised to power 6 joule, and then 1 gigajoule, that is 10 raised to power 9 joule. So these are the SI units or bigger unit of work, and we know that the CGS unit of work is, that is erg, and 1 erg, we know that work done is equal to F into S. CGS unit of work, that is erg, and the CGS unit of force is dyne, that is 1 dyne into centimeter, that is the SI unit of displacement. Now even you can define the CGS unit of work like The work is said to be 1 erg when a force of 1 dyne displaces a body through a distance 1 centimeter in its own direction. Now the next is relationship between joule and erg. Next is relationship between joule and erg. Students, as we know that 1 joule is equal to 1 Newton into 1 meter. But 1 joule is equal to 10 raised to power 5 dyne and 1 meter is equal to 10 raised to power 2 centimeter. So 1 joule is equal to 10 raised to power 5 dyne into 10 raised to power 2 centimeter. So this is 10 raised to power 7, 5 plus 2, 7 dyne centimeter, or we can say that 1 joule is equal to 10 raised to power 7 erg. So with this we have finished with this topic, that is work. Now move to the next topic, that is power. Now power is the rate of doing work, and power is also a scalar quantity. Power is a scalar quantity. Now measurement of power is represented with letter P, and this is equal to work done upon time taken. You can write it W upon T. This is what power is. Now the next is the relation between the power and the average speed. As we know that, I'm just writing here, the relation between power and average velocity. As we know that work done is equal to F is what? Power is equal to work done upon time, that is F into S upon T. So displacement upon time, that is force into velocity, average velocity. So this relation will help you to solve the numerical problem.